Welcome back to the Dr. Liu VCE Physics channel. In this video, we'll review the 2025 NHT Physics exam, focusing on questions related to magnetic forces. My explanations may not be perfect, so if any teachers, parents, or students notice any errors, please feel free to offer your feedback. A current-carrying wire loop placed in a uniform magnetic field B experiences a net magnetic force. The elemental magnetic force on a wire segment is dependent on the current, the segment length, and the magnetic field strength B. Although the net force on a closed loop in a uniform field is zero, the forces on opposite sides create a torque. This torque, which tends to rotate the loop, is dependent on the current, the magnetic field strength, and the geometry, such as the width of the loop. Conventional current flows from the positive terminal to the negative terminal of the power source. Following this path, the current in the coil segment Lm flows from point L to point M. Using the right-hand rule for magnetic force, we determine that the magnetic force acting on segment Lm is directed upwards. Students are undertaking an experiment on electrons entering a region of uniform magnetic field, B, at a speed, v, as shown in the diagram below. The direction of the electron is perpendicular to the magnetic field. The path of the electron inside the magnetic field is circular with radius, r. The strength of the magnetic field, B, is kept constant. Since the electron is traveling at a low speed, relativistic effects can be ignored. In this scenario, the magnetic force acting on the electron serves as the centripetal force. By combining the magnetic force equation and the centripetal force equation, we find that the radius of the circular path is directly proportional to the electron's speed. The cathode ray tube consists of an electron gun producing electrons, which are accelerated by an electric field produced by a 5.0 kV potential difference. The electrons then pass into an area containing both an electric field and a magnetic field, B, each of which can be independently varied to change the path followed by the electrons. The whole apparatus is encased in a glass envelope and evacuated to a low pressure so that the electrons can move freely through the tube. The strength of the electric field, E, is defined as the voltage difference, or electric potential difference, per meter of distance. Since both the voltage, V, and the distance, d, between the electrodes are known, we calculate the electric field strength by simply dividing the voltage by the distance. The net force on the electron must be zero for it to move undeflected. Since the magnetic force on the negative electron is determined to be downward, using the right-hand rule for the conventional current, or by applying the Lorentz force equation, an opposing upward electric force is required for balance. Because the electron is negatively charged, the electric field must point downward, opposite to the required force. For the electrons to pass straight through the perpendicular magnetic and electric fields undeflected, the electric force must be perfectly balanced by the magnetic force. By equating the equations for these two forces, we can calculate the speed of the electrons that are transmitted. If electrons travel at a speed slower than the selective speed, the magnetic force decreases. Since the electric force is constant and directed upward, it now overcomes the weaker magnetic force. Consequently, the electrons experience a net upward force and are deflected upward. This section focused on the forces exerted by magnetic and electric fields on moving charges and current-carrying conductors, contributing 12 marks, 10%, to your total score. Current and torque. Understanding that the torque driving a DC motor is directly proportional to the magnetic field, current, number of turns, and coil area, force and motion, using the right-hand rule, or Fleming's rule, to predict the direction of force and rotation on current-carrying wires. The velocity selector curve. The radius of the circular path is directly proportional to the electron's speed. Calculation. Determining the electric field strength and the precise selective speed required for electrons to pass undeflected. Analysis. Identifying the correct plate polarity required to balance the magnetic force and predicting the deflection path for electrons moving too slowly. Should you require assistance, please feel free to connect via WeChat or WhatsApp and send an email. Thank you for your attention. Kindly note the details of Dr. Liu's VCE Physics, Chemistry, and Biology channels.